Scientists reviewed all these submissions and picked out 2 for special recognition. So I'm about to announce, I hold in my hand the name of the winner of one of the Best Student Paper Awards for the conference. Before I announce it, though, I would like to ask the next speaker to raise his right hand and repeat after me.
Okay.
I solemnly affirm
that
I will faithfully correct
all
quantum errors,
real
or imagined, and will to the best of my ability
and will to the best of my knowledge
preserve, protect, and defend the quantum computer.
the quantum computer.
Congratulations. By the authority bestowed upon me, I bestow upon you the Best Student Paper Award. And our next speaker will be Haah, local stabilizer codes in 3D without logical string operators.
Thank you very much. It's my great pleasure and honor to receive this prize. And I would like to thank my advisor, John, because it was like a year ago or half ago, too, that I was working on the wrong model. I was wrong. I proposed the model, and it turns out to have a string operator like after 3 months of calculation. But still, John expressed genuine interest to my work, and that encouraged and helped to accelerate and to seek further tries. So let me begin. It's all about the quantum hard drive. We wish to find the noise-free subsystem or subspace from a large Hilbert space, from a physical system. But we want to have some manipulation ability on that. For example, there is a billion years of old entangled system, the ground state electrons in the helium atom. But we have no ability to access them. So it is not interesting to us. We wish to have manipulation on that. My focus is on a many-byte system that have so-called local indistinguishability, or called topological order, which means it has a ground state, degenerate ground state, more than 2 ground states, but they look exactly the same when you look at it locally. But this kind of steps, and they are for a long time known to stable at 0 temperature. Kitaev mentioned briefly in his paper, and recently, just last year, Bravi, Hastings, and Michalakis proved, actually, for proper Hamiltonians, such a degeneracy and the gap remain stable under any arbitrary perturbations. So it defines a quantum phase. But the word topological order should not be confused with a topological quantum computing with anyons. Topological quantum computing with anyons concerns about the excited states. We encode the quantum information into the excited states, the configuration of defects, anyons. But here, we are mainly focused on the ground space of the Hamiltonian. Why is this problem hard? Well, the prototypical example of the topological order is obviously the two-dimensional Kitaev's code, which just 2 terms in the Hamiltonian. They are all commuting. So yeah, and it has 4 degenerate ground states when the model is defined on the torus. And such a 4 degeneracy comes from the non-trivial topology of the space it is embedded. And because such a topological consideration leads to conclude that the ground states are locally indistinguishable. But at finite temperature, there may be some defects, and there has to be some defects. And since we are able to operate on the anyons, we believe to do so. So anyons can move around. But if we can move the anyons, then nature can move. And thermal errors are unknown to us, and they will drag the defects from arbitrarily far apart. And if the defects are created and propagated for long distance and reannihilate in a non-trivial way, then it is as if there has been some non-trivial action on the ground space, which means the encoded quantum information at the ground space has been corrupted. It's been flipped. Further, this phenomena had happened for all low-dimensional models. By low-dimensional, I mean 3 or 4, 3 or 2. But around 10 years ago, in a paper by Dennis et al., the 4-dimensional torus is proposed, and 3 or 4 years ago, it has been rigorously proved that it has a self-correcting property, meaning that the relaxation time of an encoded state grows exponentially with a system size, provided that the temperature is sufficiently low. So there has been a lot of questioning in what will happen in 3 dimensions. Bacon proposed the model in the 3 dimensions, and it seemed to work via the mean field theory, but this Hamiltonian is non-commuting, so we have no idea what the spectrum looks like. It may not be even gapped. But here's a possibility. Each term defines a quantum code. Each term is a generator for the quantum code defined in a 3-dimensional torus with 2 qubits per site. And you can easily verify that it defines a stabilizer code. Every term's commute. So energy spectrum-wise, everything is known. It's just equally spaced and never, the gap does not collapse in the thermodynamic limit. And it has no frustration. And we can prove that it has no string-like operator, the meaning of which I will describe in detail later. The key concept to understand this model is to understand the string segments, not the strings. Well, I will prefer to define a string in terms of string segments, as you will see later. And it has a very exotic degeneracy. When the system size has a lot of powers of 2, the degeneracy grows exponentially. But if the system size has in a particular shape, then it drops to constant. Okay, let us begin from the very primitive setting, because this is the way I found that model. From the yesterday's TOS tutorial, we know that studying stabilizer codes is equivalent to study the classical codes over the operator algebra. Well, to be specific, the Pauli operator group. And you can parameterize any Pauli operator by bit strings, and you can interpret the multiplication of the operators in terms of the modulo 2 addition of such a bit strings. Further, you can even encode the commutation relation into some symplectic structure. So every language, well, statement in the stabilized code can be described in terms of symplectic binary vector space. More generally, if you consider QDIT with a prime dimension, then the description becomes the linear algebra over that final field. So what's code in this language? The commuting set of Pauli operator corresponds to the null space. By null mean where the space on which this symplectic form vanishes, and we call that a stabilizer group. And the corresponding symmetric group, when you think of the codes as some representation of a Hamiltonian, then the symmetric group of that Hamiltonian corresponds to so-called the logical operators. Okay, what should I do with that? There may be several qubits per site. that's very general setting, so I don't assume anything about the number of sites, number of qubits per site. And there are some finite number of generators for each site. And since I don't want to describe the model with the infinite data, so I assume the translation invariance. And I want to have no single site logical operator, which corresponds to the local indistinguishability of the ground space. And since we want some Hamiltonian where the defects cannot move, where the string operator is not absent, so we want some model with no obvious string operators. But this is too general, so I have to simplify myself to the case where t equals 2, just one generator for x type and one generator for z, and no assumption on the number of qubits per site. And I wish to have a degenerate ground space, so the product of all terms in the Hamiltonian should be identity. This was the, you can interpret the degeneracy of the toric code in this way too. And the no single site logical operator condition translated to this. Logical operator on a single site should be identity. Well, this is too restrictive, because all we need is if a single site logical operator is found and we require that the element should be in this stabilizer group, but setting to be identity is more simple. And I assume further that the logical operator on a straight line, meaning that 3 coordinate axes or face diagonals or body diagonals are all identity if they are repeated single site operators. And apply the formalism of stabilizer code to these conditions, then you can translate every condition in terms of linear algebra equations. And the last 2 conditions, the logical operator on a single site be identity and the logical operator on a straight line be identity, is translated to some rank condition on the commutation matrix. So I started calculation by my desktop computer. Since I assumed 2 types of generators, one for Z type and one for X type, there are 16 corner operators. And it turns out that the not exact representation of the operators are important. The only important and the unique parameter is the commutation relation among those. Since there are 8 Z's and 8 X's, there are 64. So 8 by 8 matrix determines everything. And we need some condition so that our terms define the stabilizer code, and that translates to 27 linear equations, which can be easily solved by hand even. And we solve that equation by brute force. So 64 variables and 27 equations, and you are left with 37 free variables, which is like 100 billion, a not very big number for modern computers. So check all the rank conditions that demands the single site no operator or no obvious string operator. Then you get not an infinite, well, not a large number of solutions, not a no solutions, but there are a handful of solutions that satisfy all the conditions I described before. So here comes the first one, which has the largest symmetry group of all. I designed it from the first place that they are commuting, so you don't have to check it manually, but if you wish, you can. And there's some property that I didn't demand. There is some duality between Z operator and the X operator, and this duality reduces a lot of calculation in practice. For example, if you flip the body diagonals, like ZZ and II, and replace the first qubit and the second qubit, and relabel Z and X, then you get Z from X and X to Z. They are exactly dual. Okay, I designed it so that it is topologically ordered and it has no string. But I didn't prove anything. It was just a convenient requirement, necessary conditions. It's not sufficient, so we have to check whether it really works. And there's a quite annoying question. What do you mean by string? I didn't define string. So well, let us answer the first question first. The first question is it topologically ordered? And the answer is yes, meaning that there's no local observable that distinguishes ground states. So logic goes like this. If an operator is local, then when restricted to the ground space, its action is proportional to the identity element. And how do you prove that? The claim is any Pauli operator support commuting with all stabilizer generators, then the Pauli operator itself is a stabilizer. But yeah, and this implies the first statement because any operator has a linear expression in terms of Pauli operators. And this equation is linear. And because of the duality, I don't need to check for all the possibilities. I just focus on the X type only for convenience, or Z type equivalently. OK, all you need is this tool, the eraser. If the question mark is one of these four operators, well, I means I tensor I, actually, and xi is x tensor I by convention. And if I impose that, it has to commute with zz, and what's the possibilities? And you should be able to figure out. The answer is either identity x. What if I impose two conditions? It has to commute with iz and it has to commute with zi, then it's nothing. It's always be identity. And by similar manner, if I pose lower two conditions, then question mark should be identity too. Okay, what does that? What is it good for? So I promised to show that any X-type operator that commutes with Z-type stabilizer generators are stabilizers themselves. So suppose a really big box, well, big but finite, and check the commutativity with the Z operator here. Since this corner has to commute with this corner, which means this corner is either identity or xi, no other option. But this xi is this xi too. So if you multiply this generator to here, if this side turns out to be xi, then you can make this side to be identity by acting on inside of this box. So I can keep doing this. So whenever I see a vertex from this side, then I can always make them as identity by multiplying this. So I would get a Pauli operator of support that looks like this. But look at this side. This side has to commute with iz and zi. By previous exercise, you know that this is identity. So you keep doing that. And then you will erase the left-hand side vertical square. And look at this side, and you apply the same logic here using this edge. And you know that this is identity. And everything disappears. So I started from a very general X-type operator and imposed that it has to commute with this and imply that it is a product of the right-hand side. So it is a stabilizer. All right. Now, for the no-string rule, here's a challenge. The squares represents the elementary excitations when there is a single bit flip on the first qubit or a second qubit, and the black dots represents the flipped stabilizer generators. Can you make a pair, just two defects out of this? Well, the answer is no, and I will show in detail how to prove that. So here's an old question. What do you mean by string? We know there's a string operator in the Tory code because we string-like operator. We named some operator string we haven't defined string yet. For example, this looks like a string. Combination of two strings that looks like string. 3, okay. Is it surface or string? It's not obvious. So we need some different definition for a string. So here I propose most natural definition, I think. So the problem was that in the discrete lattice, one-dimensional object is not well defined. You can tell a one-dimensional object when you see it, but it's not a definition. And we need to, in general, we need to deal with a family of Hamiltonians, and I have no idea. So we need to go to some finite setting. We can't deal with some infinite things. So what's a string segment? It is a finite supported Pauli operator that creates at most 2 locations. Here, 2 is important because any conceivable string has 2 ends. And 3 more terminologies. The anchors mean that the boxes that envelope excitations, and width is defined to be the size of the anchors, and length is the distance between the anchors. The point is, there's no geometric constraint. The string segment can be like a sausage or some weird knots or whatever you want. The only condition is that it creates only excitation in 2 locations. But it's not the end of the story, because if you consider an identity operator, then it is trivially a string segment because it creates no excitation. Therefore, it creates less than 2 locations. So we need to get rid of such a triviality. And trivial conditions are rephrased like this. Whenever you have a string segment, it has a equivalent Pauli operator whose support are separated by multiplying the stabilizer generators. And if you want to be more sophisticated, then you can say that trivial string segments only creates trivial charges that are possible to create locally. So let us see some examples. In the 2D toric code, when you apply z, z, z like in this manner, then it creates a defect at the end, 2 locations. So it conforms with the definition of string segments, and it is. And you can show that it is non-trivial. There's no string segments that you can cut out this region. You have to connect somehow between 2 yellow squares. It has width 1 because width is defined to be the size of the anchor, and length is potentially infinite. It is not bounded from above because you can put as many z's as you wish. Okay, what about then 2D Ising model that we understand really very well? It is an example of stabilizer code because any classical code is. Suppose a black region has flipped spins, then it will create a domain wall along its boundary. And in order for such a string segment, this is a string segment because it creates excitation in 2 regions where the yellow squares cover. And you can show that 2 anchors must be adjacent. Otherwise, each excitation in each square can be created locally. So it has some non-trivial width, the size of the anchor, but length, the distance between 2 anchors should be always 0. So here's the formal no-string rule for my model. Statement is that a string segment of width W is always trivial provided that its length, the distance between anchors are sufficiently large. And the boundary is not too severe, it's just a polynomial. It's just linear. And this will be important when you want to show some dynamic properties of this model. So how do we prove that? Well, we can just follow the definition because we have good definition. We start with an arbitrary string segment and show that there is an equivalent disconnected string segment by multiplying suitable stabilizer generators. And the trick is that any string segment will be reduced to union of 3 flat ones, and I will show that each flat ones are trivial. So we use the eraser again. You just test the commutativity with Z operators. And since this edge has 2 independent ones, and that implies you can eat up the lower front part of the box. So you can transform this box to here. And that trick is used for the reduction. For a given general string segment, you can reduce some flat ones. Flat means parallel to the coordinate axis. And given us flat ones, you can argue further using the same argument that using this independent edge, you reduce to the second figure. And here's some slightly complicated calculation. If 2 adjacent operators are commuting with IZ and ZI and II and IZ, then there are only 4 possibilities. And since the model is translation invariant, it has to make some consistent combination of the operators. And you realize that at most after 2 sites, it has to be identity eventually. And you keep inductively argue line by line by eating up more and more sites, and you end up with a small triangle on the left and a vacant thing on the right. So we have disconnected. We are done. So what does that mean? No string means you can't drag the defect, actually. If you can drag the defect from here to there, then the combination of those are represented by string segment, and this is not allowed. So the dragging defect is impossible. It's protected by the Hamiltonian. So let me finish with this exotic feature of this model. Here's the K, the number of encoded qubits, as a function of system size, L by L by L, L cubed. And it looks like something we have never seen before. But you can prove some formula, and it turns out that the calculation reduces to GCD calculation over the field of 4 elements, where the T, remember that T is not the exponential 2 pi I over 3. It lives in a extension field of binary field. So it has no connection to the complex numbers. But anyway, you can efficiently calculate the K using this formula. Right? Let me just finish here by summarizing the basic properties of this model. Thanks for listening.
Questions for Changwon?
So what happened to the other 16 codes? Are they interesting too?
The 7 models that are numbered like 11 to 17 has strings but has width 2. And 3 other models have no strings, but the bound on the length of the string segment is exponential. It's not as good as this linear bound. And for other 6 things, I don't know.
In Kataev's 2-dimensional surface codes, you can load it with many logical qubits by removing stabilizer generators, and each generator you remove becomes a logical qubit. If we remove a plaquette type operator there, we can identify that, let's say, with logical Z, and the logical X becomes a string-like operator that connects that plaquette to the nearest other plaquette, which may be the entire surface itself if it's a bounded surface. So when we create logical qubits this way, we necessarily create string-like logical operators, even if we just ignore the entire volume itself. In your codes, if you were to remove a cube out of a volume, and call that a logical operator, there must be a corresponding commuting partner to it that anti-commutes with that three-dimensional volume and does something else. Is that object string-like, or what is the geometry of that object which anti-commutes with the cube, which you've removed?
Very interesting question. I thought about that for a moment, but I don't have concrete answer for that. It is somehow related to the question that how do we define this model with the open boundary? But there could be many boundary conditions that you can impose, and there could be many the Pauli operators that you can put on the boundary, and I have no idea how to classify them. And even further, because K has really complex number theoretic dependence on the system size, I don't have a complete list of logical operators too. So for asking the geometry, it is far beyond.
Do you see a way to extend this model so that it will also support computation beyond memory?
I personally didn't much think about that. Perhaps one can exploit the feature that it has extensive degeneracy, but that was not main focus of my research recent days.
Okay, last question.
So just following on from all those comments, wonderful talk. I think you can do computation in this. If you cut a torus through this, you can have a logical operator that's a membrane in the torus, and if you have alternate logical qubits that are spheres, you can punch holes around that and drag strings and surfaces, and I think you can do computation in that scheme. So it'd be great to talk.
Okay, thank you.
How do you fasten your shoes? Velcro?
It's just strings.
Okay, let's thank John Wan again. Let's bring up the next speaker.